take a look at case 3. So we're going to have A and B be non-zero vectors in n space such that theta, which is the angle between them, is strictly between 0 and pi, so that they are not parallel vectors. Okay. So then when that's the case, we can form a triangle with A and B as essentially adjacent sides. So I might have something that looks like this. A and B. Now, of course, triangles are made up of line segments, but I'm going to just essentially ignore the direction that this is pointing, but keep the fact that here's the angle between them. Okay? And then if I just connect the tips of those vectors with a third side, I'm getting a triangle. Notice if I do that, here I used the vector that pointed from the tip of B to the tip of A. Notice that makes that third side A minus B. Now, I drew a picture here, and in this picture, theta was acute. I've mentioned we can't do a proof by picture because anytime you draw a picture, you're making a specific choice. But notice, if this was A and this was B, so that theta was a right angle, I could still form a triangle. And the third side, I could still make be A minus B. And if I had A here and B here, so that theta was an obtuse angle, I could still form a triangle, and the third side would still be A minus B. So I'm using a picture so that I have a triangle to look at, but I am not making a specific choice that I have an acute triangle or a right triangle or an obtuse triangle. All I'm saying is I have a triangle. Okay. And I'm just going to say that then the third side is determined by A minus B. Okay. Again, technically the sides are just the line segments, ignoring the directions. The directions are important just in determining that I've got this angle theta between A and B. Whatever it is, I'm going to have one of these pictures. Okay. Now, I can use the law of cosines. I'm going to just remind you of what the law of cosines states in general. Okay. So if I have some triangle with angles A, B, and C, and I label the sides, opposite A is side A, opposite B is side B, and opposite C is side C. Okay. The law of cosines says that C squared, this length squared, is equal to A squared plus B squared. Now if I stop there, that would just be the Pythagorean theorem. That's what I would get if angle C happens to be a right angle. If not, I get this extra term of minus AB times cosine of C, where C is the angle that I have right here. Okay. That holds for any triangle. So it holds for acute triangles, it holds for right triangles, and it holds for obtuse triangles. Notice, if C happens to be a right angle, cosine of C is just 0, that term drops out, and I've got the Pythagorean theorem. Okay, so I can apply the law of cosines here. So by the law of cosines, and you know what? I'm actually going to rewrite this at the top because I'm going to then be simplifying from there. So I'm going to say by the law of cosines. Now notice side C is opposite angle C. Now here the angle that I know is theta. The side that's opposite it was determined by A minus B. So that side length is the magnitude of A minus B. That's going to be that side length squared. And that's going to equal this side length, squared. So the lengths of these sides will be the magnitudes of the vectors that are determining those sides, plus the magnitude of B squared. and then minus 2 times the magnitude of A times the magnitude of B times cosine of theta. So that is what I get, regardless of which picture I actually have. I just need to know that I had a triangle. Okay, and you'll notice, of course, these are the magnitudes, which are the side lengths. So I'm not squaring vectors here, I'm squaring the magnitudes of these vectors, which are the lengths of the sides. Excellent. Now, what's interesting is I don't need to prove this equation. I know the law of cosines is true. So I can work with both sides of this equation because I'm not trying to prove that it's true. I know it's true. What I'm going to do is simplify it and try to ultimately solve for the dot product of A with B. So to do that, I'm going to take these magnitudes squared, and I'm going to just rewrite those in terms of the dot product, because I know if I have a magnitude squared, it's the dot product of that vector with itself. So this is A minus B dotted with A minus B. This is A dotted with A. This is B dotted with B. And here, since I don't have these guys squared, I'm going to just keep this piece as it is. Minus 2, magnitude of A, magnitude of B, cosine of theta. So now I want to work this out. Now if I look at this, I'm dotting a difference of two vectors with itself. Now, if this wasn't a dot product, if this was just regular multiplication, and these weren't vectors, these were just numbers or variables, if I'm multiplying something with two terms times something with two terms, I would FOIL it out. Now, can we FOIL a dot product? Well, the answer is yes, because FOILing is really just applying the distributive law. I'm going to distribute this A to both this A and this minus B, and I'm going to distribute the minus B to both this A and this minus B. So the distributive law holds, so I can go ahead and do that. I'm going to write it out as A dotted with A minus A dotted with B. So there I've distributed the A to both pieces. And then minus B dotted with A. And then minus a minus is going to become plus B dotted with B. And that's equal to A dotted with A plus B dotted with B minus 2 magnitude of A, magnitude of B, cosine theta. Okay. Now, is negative A dotted with B the same as negative B dotted with A? Absolutely, because the dot product is commutative. So A dot B is the same as B dot A. So I can say that this is A dotted with A minus 2 copies of A dotted with B. Just like if I were FOILing out and these weren't vectors, if I was just multiplying, the outsides and the insides are often like terms. Okay. Plus B dotted with B, and that's equal to A dotted with A plus B dotted with B minus 2 magnitude A, magnitude B, cosine theta. Excellent. Now once again, I know this equation is true, so I'm allowed to do the same thing to both sides. So I'm going to subtract A dotted with A from both sides, and I'm going to subtract B dotted with B from both sides. And what I'm going to be left with then is negative 2 times A dotted with B is equal to negative 2 times the magnitude of A times the magnitude of B times cosine of theta. Let's divide both sides by a negative 2. And what do we have? A dotted with B is the magnitude of A times the magnitude of B times cosine of theta, where theta is the angle between A and B. Kind of cool. So for this third case, I didn't start with this result and try to prove that it was true. I started with something that I knew was true, which was the law of cosines. and just manipulated that equation until I arrived at this result. All right. One thing that's kind of neat, if I look at this formula, and remember, I can rearrange it to solve for cosine of theta. So cosine of theta is A dotted with B over the magnitude of A times the magnitude of B. I also know that theta is in the interval from 0 to pi. So it could be 0 or pi over 2 or pi. Those are the three quadrantal angles that are my possibilities. But then it could be acute or it could be obtuse. Okay? And if I take a look at things, if I look at where theta lives and the sine of cosine of theta, if theta is between 0 and pi over 2, cosine of theta will be positive, because cosine of 0 is positive 1, and the other angles in that interval are acute angles. I get a positive value for cosine. If theta is equal to pi over 2, theta is going to equal 0. And if theta is between pi over 2 and pi, not including pi over 2, cosine of theta will be negative. Okay. That's because I either have an obtuse angle or a straight angle with theta equaling pi and cosine being negative 1. Kinda cool. Okay. So I can pretty much tell whether I'm working with an acute angle or 0, or an obtuse angle or pi over 2, by looking at the sine of cosine of theta. But if I take a look at it, cosine of theta is defined by this. The denominator is always going to be positive. So the sine of cosine of theta, the SIGN, is going to be the same as the SIGN, the plus or minus sign of A dotted with B. So the sine of cosine of theta is the same as the sine SIGN of the dot product of the two vectors. So that gives me a very quick way of telling just at a glance whether two vectors are going to meet and form an acute angle, a right angle, an obtuse angle, and I can pretty much tell by inspection if it's one of the extremes that it forms 0 or a straight angle, because in that case the vectors would be multiples of each other. Okay. So, for example, if I had A equals 1, negative 5, 2, and B equals 3, 4, negative 7, A dotted with B is equal to 3 minus 20 minus 14. That's negative 31. That's a negative number. Now, looking at this, these vectors are not parallel. This is not a multiple of this vector. So, I know that the angle between A and B is going to be obtuse. It's not pi, but it's got to be bigger than pi over 2 because its cosine has to be negative. So that's kind of a neat consequence of this theorem that gives us a very useful application for the dot product, that we can use it for finding the angle between two vectors.